Hello, Erica.
Yes, apologies, everyone. We had some we were having some issues or technical difficulties, but we think those have been resolved, and we are going to go ahead and get started. Dan Arthur, if you want to go ahead and get started, and I will.
Super.
With Dan Jarvis.
Okay, I don't see Dan Jarvis on, but
I will get him there if you want to go ahead and start.
Yep. So hello, everybody. This is our third webinar in the series on the Class 2 injection control underground injection control program. The one today is on step rate testing. So hopefully, if you as you go through this and have questions afterwards or whatever, you can get those to Josh or I. But part of the reason we wanted to do this is just speaking historically from my EPA days back in the 80s and so forth, when we were really looking at step rate tests. I would say that from then to now, we've learned a massive amount. I would say early in the UIC program, we took these tests very basically, and what we've learned over time just in doing so many of these tests and just seeing what not only us but you know, the EPA regions and states and others have done and learned, we wanted to make sure to get some info out. I'll tell you, especially Josh and I, in doing these tests, we've just seen many tests not done to a very high quality, having lots of things that can add challenges and difficulty in interpreting the tests. We've also seen things that I know Josh will get into, where you have, large, thick formations with different properties, and sometimes the data that you get can fool you a little bit. So within this, I'll just say, there's lots going on here. I'm sure, many of the regulatory folks in here have seen a bunch of these. If you haven't, though, this is a tough deal, especially in today's time where we're moving away, say, from some of the deeper formations in some areas, going to shallower ones, and looking at rate and so forth. So I see a lot of changes developing in this area, and making sure that you do these tests right is just critical. And that's especially a challenge when you get out in the field and you look at this, and you may be on a test where you know that it's critical to keep a constant rate and to address friction losses and all those things. And maybe to keep that rate, you got a truck driver that's doing that by holding his foot on the gas pedal. I mean, we're sometimes working with some really challenging equipment and technologies that are certainly advancing over time, but a lot of details that we need to stay abreast of and continue to try to keep improving. So with that, Josh, I'm going to turn it over to you.
All right, thanks, Dan. My name is Josh. Dan and I have worked together for 10 years now, and during that time, we've done a lot of step rate tests, and this is some of the findings that we understand about those. So, step rate testing basics. Generally, we find that the default fracture gradients are generally conservative and lower than the actual fault gradients you would find in injection zones. So, step rate tests are a common test used to determine formation parting pressures for purposes of establishing the maximum allowable injection pressure and the rate that you get with that. So regulatory guidance generally doesn't acknowledge the challenges involved with performing or interpreting step rate tests. And we have seen this in so many cases where actual step rate tests seldom look like the examples they put into the textbook. So with that in mind, testing procedures are critical, and you have to have a proper interpretation and a thorough analysis of the data you receive. And going on, supplemental data can aid with interpreting those results. And we're going to get into some of those methods that we can use to supplement a report and analysis. So in general, step rate tests are just utilized to determine the fracture parting pressure. And that is done through this method here. Analysis process begins with plotting the step rate injection in barrels per minute against the bottom hole pressure after it is stabilized at the end of each step. Typically, the duration of each step is 30 minutes. I've seen 60-minute steps before, but that depends on the state and permeability of the formation. But the key here is to observe the two trends that develop. One is the pre-fracture trend line. This is usually a relatively straight line, and the post-fracture trend line, which develops as the slope decreases, indicating that the reduced pressure response per unit of injection that is being inserted. So the fracture parting pressure seen here at the intersection occurs between the intersection of those two lines. This is a typical setup that we would recommend. This is a frac pump. The step rate tests need pumps capable of injection of the well at controlled, increasing flow rates. So frac pumps are able to do that while recording the flow rate and the pressure from the pump. And these are critical for accurate interpretation during analysis. So frac pumps can get very high pressure, and you can put them in series, so they're capable and intended to exceed the fracture formations, the formation fracture gradient. So this is a wireline and lubricator setup. This lubricator goes on top of the wellhead. It's essentially a pressure type pipe mounted up there to allow tools to enter the wellhead under pressure. It provides the chamber to house the tools while it is being lowered into the well. And then this is our logging truck. We highly recommend that downhole pressure and temperature is recorded with backups. But that comes with a couple caveats. Downhole tools require power, and if that is the case, they can be done via the wireline or internal batteries, which are most people call the bomb style pressure bombs. But we recommend also real-time readout of the bottom hole pressure, and that is only capable of wireline connected tools. So anytime a logging surface is capable of providing real-time bottom hole pressure, we recommend taking that option. So this is a couple drone shots of a facility during our testing. You can see the storage here is, this is a better shot. The storage here is manifolded into our buffer tanks, which is going into our frac pumps and into the wellhead. We have our logging truck set up here and our lubricator here. This is a good setup. We have excess storage of injectable fluid ready to go. And this provides no issues during transfer. If those arise, we shut down the test, and sometimes we'll have to restart 24, 72 hours out after, depending on the formation reservoir pressure and how quickly it returns to the connate pressure. So going on, the general guidelines come from the EPA, from Class 1 guidelines. The Region 8 is the most thorough guidelines provided, and those go through the importance of determining the fracture pressure, and the intended goal of each guideline is to prevent unintended fracturing during injection. The guidelines recommend initiating the test at a low injection rate and progressively increasing it in equal steps, allowing each rate to stabilize before proceeding to onto the next one. These guidelines provide a detailed step rate test procedure based on percentages of your maximum allowable rate, including the selection of appropriate injection rates and durations for each step. And typically they recommend that formations with permeabilities less than 10 millidarcies, those should be conducted at 60-minute step durations, while for higher permeability formations, a 30-minute duration is recommended. Since we're dealing with injection wells, we wish to have wells with high formation permeability. And I've included the reference for these out here below. So I've surveyed several state guidelines that are available online, and these are the key recommendations across those. The test should be done in preparation, and I would recommend that you ensure that the well is shut in for an adequate period to stabilize bottom hole pressure near that of the formation pressure. The stabilization is crucial for obtaining accurate results. Begin with low enough injection rates and increase them in equal steps. Each step should be maintained for the sufficient time to achieve pressure stabilization. And these range from 30 to 60 minutes, depending again on formation permeability. The states typically require data recording, record of the injection pressures and rates at each step. We recommend, and the states do too, that you utilize a surface pressure and bottom hole pressure measurement to ensure that the data is reliable. And the analysis requires that you plot out the stabilized pressures against the corresponding injection rate. The point of this is to find the deviation from the linearity on the plot, and that will indicate the formation fracture pressure. So this is, pardon me for the wall of text, but there are some differences between the state guidelines that we will highlight here. Again, this is from the Texas Railroad Commission, which has published their procedures and guidelines online. This one, they note that you just ensure that proper well bore shut in to stabilize bottom hole pressures before the test. There's no guideline on 24 to 48 hours. It's to ensure that the bottom hole pressure is stabilized. And again, they note that the low injection rate progressively increase in each step, allow each rate to stabilize before proceeding to the next step. And they recommend that you maintain consistent duration, that you will record injection pressure and rate for each step. They recommend the use of both surface and bottom hole measurements. And they recommend, again, that you plot the injection rate versus time. The Utah has published theirs. They recommend 48-hour shut-in. Again, begin with low rates, gradually increase in equal steps. Ensure the stabilization pressure at each step. Follow recommended guidelines for the 30 to 60-minute decision. And again, it depends on formation permeability. And you submit all data, included the pressure rates and your analysis to the regulatory body. The Louisiana is very thorough with theirs. One of them, their notes is that the submittals must be signed and stamped and prepared under a PE, a Louisiana PE. And these don't really guide, they recommend that they move up, shut in for a minimum of 48 hours prior to testing. And testing procedure, they begin the step, it's at the first step at 1/4 barrel per minute, and then adjust the subsequent steps to achieve at least 3 to 4 rates below and at least 3 to 4 rates above the fracture parting pressure, which they call the initiation pressure there. Then each step must reach radial flow, and that means stabilization, and that each step must last a minimum of 30 minutes. If a step takes longer than 30 minutes, also then the subsequent step should match that duration. And the data collection is similar to the prior other states. And they recommend, or require actually, that after completing the step rate test, a follow-up test, they would want you to do a radioactive tracer survey. And that is important. It helps verify that the injection fluid has entered the intended interval, and that supplements your test that you have just conducted. New Mexico has very thorough guidelines available online. They want to know through a sundry notification, the equipment specifications, the procedure beforehand, the volume and the pressure history if the well is already ongoing and injection is occurring. They want to know the last 5 years of injection, and they want to know the summary of your well treatments and any kind of historical shut-in pressures that you have for the well. They wish that you perform a MIT before the SRT. That is a mechanical injection test. Mechanical integrity test. And if there's any issues with that, you have to have those dealt with before. You have to remediate any integrity issues. And again, they note that you shut in the well for 48 hours. They have general testing guidelines where you begin with low rates, typically 5% of the proposed maximum injection rate, but that may not be low enough these days. Some regulators would add in a step of a 0.5 or a half a barrel per minute, and that could be pretty hard to achieve for a frac pump. So you may have to have a smaller pump on hand. But going on, aim for at least 3 steps below a half PSI foot per gradient. And that can be difficult given the gradient of freshwater column is 0.43, but we can deal with that and pump at a low enough pressure to get that done. And then you need to have at least 3 steps above the fracture parting pressure. Otherwise, a regulator may decide that the step rate test is inconclusive. So they also let you adjust starting pump rates and pressures to be lower than the current operator limits if the well is actively injecting. If you have an average injection rate, start below that. And they recommend 30-minute minimum with 60-minute durations for low permeability formations. But getting into it further into detail, there are so many factors that influence step rate tests, particularly and most importantly, stratified injection zones, and what we like to say is geologic heterogeneity. These can be from other issues that affect the step rate test, pre-existing fractures or macrofractures. These can cause the formations to be hard to interpret, where you may see multiple inflection points. And then going on, microfractures may induce zone stresses or stress fields that may affect the step rate test. Again, another thing that can occur is the viscosity and density of the step rate test fluid used may be different from what is in the well bore, and that can have effects on the early time of the well. Or if fluid viscosity and density is different in different parts of the test, that can have an effect on the hydrostatic density column. The shut-in time, pressure equilibration prior to testing is important. That's why the states are requiring you to shut in 48 hours, 24 hours before testing. And essentially, pumping consistency is important. If you have your rates jumping all over the place, your pressures will respond accordingly, and it could affect your test. The step consistency, again, is important. If you have 25-minute and then a 35-minute test step, it's not going to be consistent. You may have built up your end of bottom hole pressure to be lower or higher than actually what occurred during that step. And there are others that can influence step rate test. So that being said, the key limitations and challenges that you face can be summed up here. Most importantly, heterogeneous water intake. Some layers within the injection interval do not accept fluid at lower pressures, but they begin taking fluid at higher pressures. And this phenomenon can falsely appear as a gradual increase in injectivity, which means that it mimics the effects of a fracture, even though fracture has not actually occurred. So going on, another instance of a challenge that you'll find is the indistinct fracture parting pressure determination. In multiple layer systems, long perforated intervals, there are varying fracture parting pressures. And as injectivity increases incrementally, there is not a clear intersection point. More of a curve develops, making it difficult to pinpoint where the fracture initiation actually began. There is also the occurrence of premature test termination. In many cases, the step rate test is stopped before reaching the formation's parting pressure, particularly in wells with long perforated intervals. In these wells, The long perforated intervals allow for multiple entry points of injected fluid. And as a result, linear injection rate versus trend may persist. And that may lead to false assumption that fracturing has not taken place. Going on, step rate tests are applied as a simple and effective tool, and that is assumed. It is often misapplied to stratified, geomechanically diverse formations where the expected slope change on the pressure rate curve may not appear as expected. And this could lead to erroneous conclusions and formation integrity issues. The key limitation is that the step rate test is used throughout regulatory guidelines, even for multi-layered and stratified systems. Here I'll provide an example of some multiple inflection point. This is data similar data that is conceptual for bottom hole pressure of a well, where you would see initially the effects of temperature and viscosity and density stabilizing here. And then you begin a new trend where this is the change in the slopes, the consequence of start over. This is the consequence of stratified injection interval, where you start to see fluids enter the formation and enter intervals at different permeabilities, or a shift from the matrix dominated flow to flows that are occurring in the natural formations, fracture flows. And along the line, there is actual parting pressure interpretation. This would be what we would maybe interpret as the parting pressure here in this test. But it would be best in this instance to have supplemental data to reflect the same result. In this instance, we see no discernible breakover. I've taken this case where this is not conceptual data. This is data from a client where we've taken and plotted the surface pressure, the range of surface pressure experienced during a step against each step and the corresponding pressure. Those are represented by the circle dots. And the ending step rate pressure is represented by this X. As you can see, there's a large variation in the step rate pressure on the surface pressure, but you don't see that while going on in your bottom hole pressure. The only instance of a large variation in pressures is on your initial step, when that is due to the density effect, the change in viscosity of the fluid, or the change in temperature. But once you have established a consistent flow rate, the pressure increases gradually, and there's not a lot of variation in bottom hole data. So if you are reviewing and analyzing a test without bottom hole pressure data, it's crucial to understand that their pump itself is generating variation in the data, even at high pressures. When you think you have dialed it in, you may be going in a range, your pump pressure is all over the place, whereas bottom hole, it is not. In this case, the no discernible breakover was reached between half a barrel per minute and 13 barrels per minute. And we may have concluded from this test that they should do a second step rate test at higher rates. This is labeled conceptual, but it's data collected from other permit applications in Wyoming for a stratified formation in the Tekla. As you can see, surface pressures are quite different for these tests. And that could be as a result of many things. But if you look at the Tekla, there's many sandstone members in that, and along with shell layers, and it's a multi-layered system. So the step rate tests and these in this formation, you could interpret in different ways. You would have different results in a range of fracture parting pressures, and these may not be actually reflective of what is going on downhole. Again, this is surface pressure data collected from step rate test permits. So we don't know exactly where the pressure transducer was put on the wellhead. We don't know the size of the pipeline laid to the wellhead. We don't know the general setup of the well. So there could be a lot of issues or conclusions that are not reached in this data. So given the fact that there are so many factors that influence step rate tests, supplemental data can be used in helping to interpret the fracture parting pressure. And we recommend of these, as listed below, the step temperature surveys. We go in, you establish a baseline survey, and then distributed survey during the test, and a warm back temperature profile. We'll show you a figure that discusses this to assess the heat transfer and fluid movement during and after injection. It shows how much temperature effect can occur. You are injecting cool fluids into a warm formation, so you're going to lower the temperature of that formation. And you can see that with a temperature survey. You can go in, moving on, you can go in with a spinner survey where you can determine the injection contribution at each end at different intervals or different depths. And different zones may activate, and you can determine that with something like that, a spinner survey. You can go in with acoustic tools, distribute acoustic tools on fiber, where you can determine acoustic monitoring to identify fracture events and determine flow pathways during and after injection. You can take bottom hole pressures and compare them across other tests, and then analysis of bottom hole pressures and injection responses across multiple step rate tests to assess consistency and see if there's any variabilities that have developed. You can take a look at core and log data and see if you can get a good idea of permeability, and maybe you can go on further with advanced imaging techniques to better understand the reservoir heterogeneity and fracture behavior. And then again, tracer surveys and spinner surveys can be used to go map out injection flow and identify potential pathways of migrating fluid. And there are new tools developed where you can do fracture migration analysis, where the tool integrates multiple arrays of acoustic data with the fracture anisotropic fracture evaluation. It can determine migration pathways. I have an example of that too. So this is the first example of using a spinner survey to reveal how the reservoir will begin to accept fluids at higher pressure. Here we have a test that was conducted on a well in Wyoming, where we started a temperature test at 1.6 barrels per minute, or I'm sorry, a spinner test. And as you can see, a large portion of this formation is accepting, or I'm sorry, a small portion of this formation is accepting a large portion of the injection volume. But if you increase that rate to 5 barrels per minute, other portions of that formation begin to accept fluid. This can be seen on this test, and same here, where once you increase the rate here in red and pink, lower portions of this formation begin to accept fluid. At higher rates, the distribution of the injection increases across the vertical interval as the injection rate increases. This is a Schlumberger STAR log tool. It provides isotropic fracture analysis. In this instance, ran on the same well. You can use it to show that the formation is comprised of layers of varying brittleness, and that you can get no indication of structural fractures or indications of structural fractures. And in this case, the stress profile indicated that the fracture parting pressure or fracture pressure gradient in that zone was greater than 1 psi. And if you are finding a breakover at 0.83 psi, 0.5 psi, 0.65 psi, and it's less than 1, this analysis will help you bolster that argument that you're making to increase your rate or to have a higher rate at the beginning your operation. Here we've taken a sidewall core and combined that with just typical triple combo and put that triple combo log and let that say where we can say multiple instances of variable permeability. The core analysis is aligned here with our log, and it indicates that throughout, as you go deeper, there are intervals of both higher and lower permeability within the unit. And the less permeability zones, as we know, will accept fluids at higher pressures, and more permeability zones accept fluid, and more permeable zones will accept fluids at those lower pressures. So as a result, step rate test data collected from this well may have a curve or an inflection point, and it may not represent, and these points may not represent the actual parting pressure, but rather, differing layers of the formation beginning to accept fluids and the ejectivity increasing as that occurs. So this is acoustic data collected using fiber optic tools available out there from maybe someone like Schlumberger, but it shows in this case, this is the conclusion of a step rate test on the top here, and the acoustic vents that are occurring following the end of a step rate test. And the acoustic vents are consistent with the formation relaxing after injection had occurred, with lower acoustic velocities below 6,000 feet. And in this case, you can see that there's a variation in velocities as the formation relaxes. This is 800 feet per second, this is 5,400 feet per second, and this is 4,800 feet per second at varying depths. Whereas this is a test taken from a well that has been fractured. And this images show that the striking black line here is the acoustic signal occurring, striking black line here is the acoustic signal. It's cohesive, it's coming from a single source, and it is a greater than 8,000 feet per second, whereas these are slow and there is no distinction in between them, as the fracture has not initiated at this well, and a fracture was intended to initiate in this well. So initiating fracture creates large coherent arrival times at higher velocities within the formation. And then this is where the formation is relaxing over time, where you do not see a striking arrival time, it's dispersed. Here is our temperature data that we like to collect. As you can see, after injection, the temperature is lowered. This is the formation interval here in blue, and it shows as the formation time progresses, the formation begins to rise in temperature. This is called the warm back. And as that formation warms back, you can see that the injection temperature, the injection fluid has entered that formation, stayed there, and have remained there. There's no cooling outside of that formation, and the fluid has remained within that. Warm back data collected following an step rate test can indicate all fluid was contained within the injection zone, and that the cooling effect can be observed out within the injection interval, and the confining zone does not see an effect. So following step rate test, you may find yourself in a position to collect fall off pressure data, and that can be used to help in your analysis. You can get the permeability of your overall injected interval, and you can determine if there's any skin factor that is measurable, and if there is a wellbore storage effect going on near wellbore. And these can be added to your analysis to account for any effects that you may have seen during your test. So this all being said, there are a lot of technical insights on step rate testing, and you'll see a reluctance from many authors to rely on step rate tests in multi-layered systems. These include, they note in Urshagi and Urshagi from 2018 that there's a variability in material properties and fracture pressures within multi-layered systems. This paper was published by Singh et al. In 1987 goes on about the concerns over step rate test design and analysis. And as far back as then, they were noting that the work could be limited and potentially misleading guidelines out there. Another one that arises is the impact of injection rate variability, which highlights the importance of keeping your rates consistent They note that if you have rates from, they just note that the errors arise from inconsistent rates and can influence the variability on follow-up test data and any kind of test accuracy that you receive. There's regulatory perspective on it, some regulatory perspective on stratified injection zones. EPA Region 5 addresses this. They note that there's challenges in interpreting inflection points and that you should couple your data with supplementary data from other tools to determine the fracture parting pressure. Recently, I recommend reading and going through this paper. It's recommended practices for determining the maximum injection pressure for saltwater disposal wells, published by SPE in 2023. And it discusses many of the issues that we talk about today, but most importantly, heterogeneous water intake in multi-layered systems is a big deal with these guys. So that gets us to some of my conclusions and some of my recommendations from our experience. I would just want to highlight that in regulatory compliance and defining the operational limits, maximum injection rate, maximum surface pressure, the step rate test is the go-to test for regulatory bodies. And the awareness of these limitations is important when generating a thorough analysis. And we can continue to innovate along those lines using more tools that are developed as we go on. So I would recommend going on that pumping services, when you're preparing for a test, be able to pump at the minimum and the maximum rates in your procedure. Oftentimes, the minimum rate is going to be now at a quarter barrel per minute or a half a barrel per minute, and that can be hard. So plan for adequate water of consistent quality, consistent temperature, consistent density. That's important for your early time tests. And then we highly recommend that you record both surface and bottom hole pressure, as those can be used in your interpretation. And then we recommend considering gathering supplemental data. These could be spinner surveys, temperature surveys, core data, any of that we discussed earlier. And then going on, we should shut in the well long enough so the bottom hole pressure is near the shut-in formation pressure, if that's possible. If that's not, wells can be flowed back. So each step should last exactly as long as the preceding step. That's crucial. And have an adequate number of measurements above and below the formation parting pressure. If you do not have typically at least 3 measurements below and above the parting pressure, the test will be considered invalid. And that's it. I don't have much else to say unless you have any questions.
Yeah, thanks, Josh. There are a few questions here. The very first one was going back to your slide. It says on slide 2 or 3, why was 0 barrels per minute rate static bottom hole pressure not plotted on the pressure versus rate chart?
Is this the one you're talking about?
Let's slide you on here. I can't see. This is a question I'm reading off the comments. What slide is this, Josh?
This is slide 18.
No, they said on slide 2 or 3.
Could you repeat the question?
Yes. It says, why was 0 barrel per minute rate not plotted on the pressure versus rate plot?
This is, again, conceptual data. I didn't include it. If you were to do that, you would put 0 in your shut-in pressure in that instance. and that can be plotted again, and you would have a trend line develop between your zero rate and your first rate. But again, that's may not be necessarily reflective of what a parting pressure would be if you see a trend line change or a change in slope, as again, those are the early times where you see a large effects from your density changes, your temperature changes, and your viscosity changes downhole. So we would recommend at that point relying on your bottom hole pressure, shut-in pressure. You could plot that at your zero intersection point.
Okay, thanks, Josh. The next question says, do you recommend the well be cleaned out and be sure the perfs are open to ensure you're testing the rock face and not the internal storage of pipe?
Highly. I do recommend that in wells that are newly completed or in wells that have been on ongoing operation or in operation for a long time where they may have skin develop. It's highly recommended.
Okay. Let's see. The next question is regarding the comment about some layers requiring higher pressures to allow injection. Do you have examples of those types of formation?
I would say off the top of my head, the Delaware Mountain Group is one, the Tekla is one, the Devonian, if you have a long interval there, could be one too.
There's a number of those kinds of formations.
Okay, thank you. Next question I have here, if you don't reach a stabilized pressure for a higher rate during the test, do you recommend extending the duration time for that rate step and the following rate steps?
That is a part of some state guidance. If you have a bottom hole pressure that doesn't stabilize in 30 minutes, then there may be something else going on downhole that you're not accounting for in your step rate test procedure. So you may have a lower permeability than anticipated. You could, so that is accounted for in some state line guidelines where you can say, yes, we waited 45 minutes to an hour on this test or this step and then moved on and have the same duration for the next step. So yes, the answer is yes.
Okay, thank you. Next question, what is a recommended practice to start a step rate test when your well doesn't hold a full column of fluid to avoid injecting air?
That is always an issue with pressure or injection wells that are low pressure or on vacuum, and you have to account for it in your analysis. You have to note that either this is your 0 point on your rate. You can have a very low pressure on your 0 rate curve, or you can say that this is wellbore storage effect going on in these initial rates as the wellbore fills up with fluid. And then you can note that the hydrostatic dynamics of that fluid column are going to change with the pressure effect, the temperature effect, the density effect, and viscosity change in the fluid that is in the wellbore versus the injected fluid. These can be noted in your analysis, and it's important to do so.
Okay. With the consideration for time and fluid on each step, is there a point with permeability that you recommend shorter steps with respect to time?
I've never seen a step below 30 minutes. So it does get difficult with some of your high volume injection wells where you're dealing with a 22 barrel per minute step. You're burning through a frac tank of fluid in 30 minutes, and it can be hard for your transfer company to keep up with that. So 30 minutes is standard minimum. I've never seen anything less than that. And I would say with your higher rates, you just have to be prepared for water transfer to keep up. Note the volumes in your procedure and be prepared.
Okay. How do you determine what is an acceptable rate and pressure to end the test?
3 steps above and below fracture parting pressure are the minimum recommendations throughout some of the state guidelines. So you find your fracture parting pressure, go on 3 steps.
I will also add one thing to that, Josh, is that, we've done some tests where, we didn't get to fracture parting pressure, but it was well within what the operator needed. So but in those circumstances, it's important to communicate, with the state agency on.
Yeah, thanks, Dan, for that. I think you kind of almost maybe answered this next question. What happens if no braking pressure is observed? How high could you go with your pressure?
I would stick with the procedure that you prepared beforehand. If that should incorporate what your requested allowable rate is. So if you're wanting 10,000 barrels per day, you're going to a test and send a proposed procedure for that test that goes above 10,000 barrels per day. If you don't see a step rate or a breakover during that test, you can say that that the well will operate below fracture parting pressure at the rates requested. And you can then, if the regulator does not feel that that is a sufficient test, use supplemental data to confirm your argument, confirm your case.
And I'll just say, Dan, that we've run across some formations sometimes that just can take a lot of fluid, and the subject well may not have a need to do those kinds of rates, but all of it can be a little complicated. So I just say, make sure you have ample communication with the regulator.
Sure, absolutely. Let's see, I think we got time for a couple more. What are some of the issues with each step not lasting the same length of time?
Well, if you have a step that is in shorter duration, your pressure may not be allowed to build up long enough. And if you have a step longer in duration, you may overpressure that step and it could get off trend because your prior steps are at 30 minutes. If you did a step that was 25 minutes, it may not have built up 5 minutes of pressure during that time. Or if you had a step that was 35 minutes, it may build up excess pressure during that time.
Okay. I think this will be the last one. This is kind of a follow-up question. They're asking, what lithology are those formations that require higher pressures to inject into?
I would say generally increasingly shaly sandstones. You're targeting sandstones when you're looking for a good formation to inject into. But as those progress into shaly, you'll start to see less and less permeability.
Okay, I got one more question here that I have time for. With the use of downhole gauges, is there concern about adding friction reducers at higher rates during the test to prevent limitations for friction pressures?
That's not a concern I've ever encountered, no. That effect wouldn't be recorded on bottom hole pressure. Regardless, it would be seen on your surface pressure. So if you're recording bottom hole pressure, then that would be not a concern.
I will say this, Dan, that when you start talking about the use of friction reducers, and I've seen that done, is you're trying to run these tests in how the well is going to operate. So if we're going to use friction reducers during a test and not use that during normal injection, that's an issue. So.
Okay.
Thank you, everybody, for attending. We appreciate you a lot. you know, as I noted earlier, our next webinar is going to be on induced seismicity. So we'll work out a time frame with Dan and Erica, and go from there. So thank you very much.
Yeah, thanks, Dan, and thanks, Josh, for your presentation. We appreciate it. I'm sure we will get that presentation out on our GWPC website pretty soon. So thanks, everyone, and have a good rest of your day.
Thank you.